Yeah, welcome back to this course. In this lecture, we are going to see the differential calculus and its applications. Now, let us start with the basic definitions of what is the radius of curvature in different forms. The first definition is radius of curvature of the curve y equal to y of x. Let y be a differentiable function. Then the radius of curvature of the curve at the point x0, y0 is defined as rho, which is equal to 1 plus y1 square whole power 3 by 2 divided by y2, where y1 is dy by dx at the point x0, y0, and y2 is the second derivative d square y by dx square at the point x0, y0. Note that if y2 equal to 0, then the radius of curvature becomes infinity. In order to avoid this, we have to redefine the radius of curvature in this form: rho, which is equal to 1 plus dx by dy the whole square whole power 3 by 2 divided by d square x divided by dy square at the point x0, y0. Suppose if the curve having the parametric form x equal to x of t and y equal to y of t, then the radius of curvature at this point x0, y0 is defined as rho, which is equal to x dash square plus y dash square whole power 3 by 2 upon x dash into y double dash minus y dash into x double dash, where x dash is dx by dt and x double dash is the second derivative d square x by dt square, and y dash equal to dy by dt and y double dash equal to d square y by dt square. Then the third definition is if the curve having the parametric representation, we are having the previous formula. If the curve is having the polar form r equal to f of theta, then the radius of curvature is rho equal to r square plus r1 square whole power 3 by 2 whole divided by r square plus 2 r1 square minus r2, where r1 is dr by d theta and r2 equal to d square r by d theta square. See, therefore, for all these things, we need the differentiable function, at least twice differentiable function, then only these things are meaningful. Now, let us see some basic examples, and we are going to find out what is the radius of curvature of some standard curves. Right. First example, find the radius of curvature of the curve root x plus root y equal to 1 at the point 1 by 4, 1 by 4. Now, given that the curve is root x plus root y equal to 1, then differentiate this curve with respect to x. See, therefore, we'll get 1 by 2 root x plus 1 by 2 root y into dy by dx equals 0. After rearranging this, dy by dx becomes minus root y divided by root x. But root y, which is equal to 1 minus root x from the equation 1. See, therefore, we can rewrite 1 minus 1 by root x, that is 1 minus x to the power minus 1 by 2. See, therefore, at the point 1 by 4, 1 by 4, y1 equal to dy by dx at the point 1 by 4, 1 by 4, that leaves 1. Right. So, dy by dx equal to minus root y by root x. See, therefore, d square y by dx square is minus d by dx of root y divided by root x, or d by dx of 1 minus x to the power minus 1 by 2. See, therefore, if you differentiate this once again with respect to x, which gives minus 1 by 2 into x to the power minus 3 by 2. Therefore, the y2, which is equal to d square by dx square at the point 1 by 4, 1 by 4, 1 by 4, that is equal to 4. Now, plug these values y1 and y2 in the formula rho equal to 1 plus y1 square whole power 3 by 2 divided by y2. That gives the value rho equal to 1 by root 2. Okay, now let us see the second example. Find the radius of curvature of the curve x cube plus y cube equal to 3a xy at the point 3a by 2, 3a by 2. Now, given that the curve x cube plus y cube equal to 3a xy, now again you differentiate this with respect to x, then it gives 3x square plus 3y square dy by dx equal to 3a into y plus x into dy by dx. After rearranging this, we get dy by dx equal to ay minus x square upon y square minus ax. And if you replace x equal to 3a by 2 and y equal to 3a by 2, then we get y1 equal to minus 1. dy by dx equal to ay minus x square upon y square minus ax. Then to find the second derivative, you differentiate this expression again with respect to x. That gives the formula d square by dx square equal to this expression. Okay. Then after replacing x equal to 3a by 2 and y equal to 3a by 2, we are getting y2. The value of y2 is minus 32 divided by 3a. Then we plug the values of y1 and y2 in the formula rho equal to 1 plus y1 square whole power 3 by 2 divided by y2, and we are getting minus 3a by 822. But the radius of curvature is always positive, so therefore you take the absolute value of this, therefore rho equal to 3 into modulus of a divided by 8 root 2. One observation, the radius of curvature is always positive. Now let us see the third example. The curve which is given in terms of the parametric representation, x equal to a into theta plus sine theta and y equal to a into 1 minus cos theta. So the curve is given in terms of the parametric form. Now either we can apply the second formula, that is rho equal to x dash square plus y dash square whole power 3 by 2 upon x dash into y double dash minus y dash into x double dash, or we can use the first formula by using this technique. Given x equal to a into theta plus sine theta and y equal to a into 1 minus cos theta, you differentiate this with respect to theta, that is dx by d theta equal to a into 1 plus cos theta and dy by d theta equal to a into sine theta. Then the ratio of these two, which gives the dy by dx, that is dy by dx equal to dy by d theta divided by dx by d theta, and replace this expression dy by d theta equal to a sine theta and dx by d theta is a into 1 plus cos theta. Now by using these identities, a sine theta can be written as 2a sine theta by 2 into cos theta by 2, and 1 plus cos theta can be written as 2 cos square theta by 2, and then already we have a outside, so therefore we are having 2a cos square theta by 2. After cancelling this, we are getting tan theta by 2. See, that is dy by dx equal to tan theta by 2. To calculate the second derivative, we use the chain rule. D square by dx square is d by d theta of dy by dx into d theta by dx, and d by d theta of dy by dx is tan theta by 2. You just plug this here, and d theta by dx is, that is reciprocal of this expression, that is 1 divided by a into 1 plus cos theta, and the derivative of tan theta is secant square theta. See, therefore this gives secant square theta by 2, and the derivative of inner argument theta by 2 gives 1 by 2. See, therefore this gives secant square theta by 2 divided by a into 1 plus cos theta. Again, by the second identity, we are having secant square theta by 2 whole divided by 4a into cos square theta by 2. Then this gives secant power 4 theta by 2 divided by 4a. Now plug the value of y1 and y2, then we are getting 1 plus tan square theta by 2 whole power 3 by 2 whole divided by secant power 4 theta by 2 divided by 4a. But 1 plus, by using this identity, 1 plus tan square x equal to secant square x. Therefore, the numerator becomes 4a into secant square theta by 2 whole power 3 by 2 whole divided by secant power 4 theta by 2. Okay. So, we have the power 3 by 2. So, after by using the power law, we are getting 4a into sec cube theta by 2 whole divided by sec power 4 theta by 2. After cancelling this, we are having 4a divided by sec theta by 2, but 1 by sec theta by 2, which is nothing but cos theta. See, therefore cos theta by 2. See, therefore we are having 4a cos theta by 2. Rho is 4a cos theta by 2. Okay, now next example is the curve which is given in terms of the polar form. That is, find the radius of curvature of the cardioid given by the curve r equal to a into 1 plus cos theta. So the curve is given in terms of the polar form, that is r equal to a into 1 plus cos theta. Now what is the formula for the polar form? R equal to r square plus r1 square whole power 3 by 2 whole divided by r square plus 2 r1 square minus r2, where r1 is dr by d theta, r2 is d square r divided by d theta square. Now you calculate what is r1, r2. r1 is dr by d theta, that is a into 0 minus sin theta, because r equal to a plus a cos theta. See, therefore r1 is minus a sin theta and r2 is d square r by d theta square, that gives minus a cos theta. Now calculate the numerator and denominator separately and plug those expression in the row formula. So r square plus r1 square equal to a square into 1 plus cos theta whole square plus a square into sin square theta. By using the formula a plus b whole square, we are rewriting this a square into 1 plus cos square theta plus sin square theta plus 2 cos theta. And after grouping this, we are getting 2a square into 1 plus cos theta, but 1 plus cos theta is r. Okay. Okay, 1 plus cos theta, which is equal to r by a. See, therefore, we are having the final expression, that is 2a r. Now to find the denominator, you calculate r square plus 2r1 square minus r2. Replace r1, r2, and then expand it. After expansion, we are having 3a square into r by a, that is equal to 3ar. So the numerator is 2ar and the denominator is 3ar. After replacing this expression in the row formula, that gives 2ar power 3 by 2 whole divided by 3ar, that gives 2 power 3 by 2 into ar power 1 by 2. Right. So next we are going to see the center of curvature and the circle of curvature of the given curve. The center of curvature of the curve is given by x bar and y bar, where x bar equal to x minus y1 into 1 plus y1 square upon y2, and y bar is y plus 1 plus y1 square upon y2, where y1 is the dy by dx at the point x naught comma y naught, and y2 is d square y by dx square at the point x naught comma y naught. And the circle of curvature is x minus x bar the whole square plus y minus y bar the whole square equal to rho square, where rho is the radius of curvature, and x bar and y bar are the coordinates of the center which are given above. Next we'll see the example. Find the equation of circle of curvature of the parabola given by the curve y square equal to 12x at the point 3, 6. Okay, solution. Now given that y square equal to 12x, if you differentiate this equation, we get 2y into dy by dx equal to 12. See, therefore dy by dx equal to 6 by y. And if you replace x equal to 3 and y equal to 6, we get y1 equal to 1. And the second derivative d square y by dx square equal to d by dx of 6 by y. That gives minus 36 divided by y cube. And if you replace x equal to 3 and y equal to 6, that gives y2 equal to minus 1 by 6. See, therefore, after replacing the value of y1 and y2 in the row formula, we are getting 1 plus y1 square upon y2 whole power 3 by 2. That gives 12 root 2. Okay, right. As we know that the radius of curvature is always positive, so therefore, even if you get the negative value, you just make it as positive. Now the center of curvature is x bar comma y bar, where x bar equal to x minus y1 into 1 plus y1 square upon y2, and y bar is y plus 1 plus y1 square upon y2, and replace the value of x, y, x, y1, y2, and we get x bar equal to 15 and y bar equal to minus 6. See, therefore, the equation of circle of curvature is x minus 15 the whole square plus y plus 6 the whole square equal to 144 into 2. Why? Because the value of rho is 12 root 2, and then whose square is 144 into 2, that is 288. And then let us see the next example. Find the equation of circle of curvature of the curve. It is not a parabola. Root x plus root y equal to root a at the point a by 4 and a by 4, and given that root x plus root y equal to root a, and differentiate this 1 by root x plus 1 by 2 root y into dy by dx. See, therefore your dy by dx equal to 1 minus root a into x to the power minus 1 by 2. After replacing x equal to a by 4 and y equal to a by 4, we are getting y equal to minus 1. To find the value of y2, you differentiate again with respect to x, that gives d square by dx square equal to root a by 2 into x to the power minus 3 by 2. After replacing x equal to a by 4 and y equal to a by 4, we are getting y2 equal to 4 by a. Now replace the value of y1 and y2 in row formula, that gives the value of the row equal to a by root 2. Now the center of curvature is x bar, y bar, and replace the value of x, y1, y2. That gives x bar is 3a by 4 and y bar is 3a by 4. And plug these values in the equation of the circle of curvature, that is x minus 3a by 4 the whole square plus y minus 3a by 4 the whole square equal to a square by 2. Okay, so this is a required circle of curvature. Next we'll see what is evolute and involute the curve. Let us consider the curve y is equal to y of x. Let P be a point on the curve y of x, and C is the center of curvature corresponding to the point. As P moves on the curve, then the center of curvature C will also move and trace out another curve gamma. Such a curve gamma or such a curve sigma is called the evolute, and the curve y is called the involute. Okay, now see, this is the definition. Very simple. Take y is equal to some curve, y is equal to f of x, and then for each and every point there will be a center of curvature. If the point P moves on the curve, then the center of curvature will trace out another curve. Such a curve is called evolute, and then the original given curve is called involute. Very simple. Now the procedure to find the evolute, the first step is, first we have to calculate what is the center of curvature x bar comma y bar, where x bar is given in this formula, y bar is given in this formula. Then eliminate the parameter from the center of curvature. Whatever the parameter which is playing in the center of curvature, you just eliminate. That gives the evolute. Right. Now, let us see the first example. Find the evolute of the curve given by x equal to a into cos theta plus sin theta and y equal to a into sin theta minus theta cos theta. So the curve which is given in terms of the parametric form. Okay, then you differentiate x with respect to theta and differentiate y with respect to theta. From this you find what is the dy by dx. So differentiate x with respect to theta, that gives a theta cos theta, and dy by theta d theta, that becomes a theta sin theta. So taking the ratio of this dy by dx equal to dy by d theta divided by dx by d theta, that gives a theta sin theta divided by a theta cos theta, that gives tan theta. To find the second derivative, use the chain rule d square y by dx square equal to d by d theta of dy by dx and d theta by dx, that is d by d theta of tan theta, and d theta by dx is the ratio 1 by a theta cos theta. After rearranging this, we are having sec cube theta divided by a theta. Okay. Then the center of curvature is x bar equal to x minus y1 into 1 plus y1 square divided by y2, and y bar equal to y plus 1 plus y1 square divided by y2. And replace x bar, y1, y2, all these expressions, and we are getting the final expression a cos theta. And similarly, replace y, y1, y2, all the things, then we are getting y bar equal to a sin theta. What is the parameter here? The parameter is theta. We have to remove the parameter theta here. So if we see the first equation, x which is equal to a cos theta, see therefore x by a equal to cos theta. And from the second equation, y equal to a sine theta. See, therefore, y by a equal to sine theta. Then square these two expressions and add it up, which gives x by a the whole square plus y by b the whole square equal to sine square theta plus cos square theta. But sine square theta plus cos square theta equal to 1. See, therefore, there is no parameter theta in this equation, right? See, therefore, x square plus y square equal to a square. That is a required envelope. Now, let us see this next example. Find the evolute of the curve y square equal to 4ax. Okay. So, for this, we have to assume the parametric form of the parabola y square equal to 4ax. So, given the curve y square equal to 4ax, and the parametric representation of the parabola is x equal to 8t square and y equal to 280. If you plug x equal to 8t square and y equal to 280, then it will satisfy the equation 1. You can verify. Now differentiate this parametric form with respect to the parameter, that is dx by dt equal to 280 and dy by dt equal to 2a. See, therefore dy by dx equal to 2a divided by 280, that is 1 by t, which is your y1. Now to find the second derivative, dy y2 equal to dy1 by dx. By using the chain rule, we get d by dt of 1 by t into 1 by 280, that is minus 1 by 280 cube. Now replace x, y1, y2 in your center of curvature, that is x bar equal to x minus y1 into 1 plus y1 square upon y2 and y bar equal to y plus 1 plus y1 square upon y2. Replace x, y1, y2, right? Then x bar, which gives 3at square plus 2a, and y bar, which gives minus 2at cube. What is the parameter here? The parameter is t. We have to eliminate the parameter t from the above two equations. So if you rearrange the equation 2, that is x minus 2a divided by 3a, that is equal to t square. Similarly, from the equation 3, y bar divided by 2a, which is equal to minus t cube. Okay. The only thing is we have to eliminate the parameter. We have to eliminate the parameter t from the last two expressions. If you raise the power 3 here, that gives t power 6. Similarly, if you raise the power 2 here, that gives t power 6. See, therefore, you raise the power 3 in the first equation, you raise the power 2 in the second equation. That gives t power 6. So, we are getting x bar minus 2a divided by 3a whole cube, which is equal to t power 6, which is equal to y bar divided by 2a the whole square. Okay. Anyway, these two are equal. See, therefore, x bar minus 2a divided by 3a the whole cube, which is equal to y bar divided by 2a the whole square. Okay. Right. So, this is a required envelope. Sorry, evolute. See, next we are going to see what is envelope of the parameter family of curves. Now let us consider the family of curves given by the form f of x comma y comma theta, where theta is a parameter. For different values of theta, we'll get different curves. And there is a curve which is touching all these parameter family of curves. Such a curve is called envelope. If there is a curve, such a curve exists, then we can say the envelope is exists. Now, the working procedure to find the envelope of a given parameter family of curve is, first one, differentiate the one parameter family of curves with respect to the parameter theta and eliminate theta from the given equations and the slope d by d theta of f of x comma y comma theta equal to 0. We'll see few examples. Find the envelope of the family of straight lines given by y equal to mx plus a by m, where a is a constant whereas m is a parameter. Now given that y equal to mx plus a by m, and differentiate 1 with respect to m, and we get left hand side there is no m, so therefore left hand 0, right hand side is x plus a into minus 1 by m square. And after rearranging this, we are getting m square equal to a by x. See, therefore m equal to root of a by x. Now you just cross multiply m in the first equation. See, therefore ym, which is equal to m square x plus a, and replace m square and m in this equation, and we are getting the nice form y square equal to 4ax. There is no parameter m involved in the final expression, so therefore this is a required envelope. What it says, this parabola y square equal to 4ax, which is touching all the one parameter family of curves y equal to mx plus a by m. Right. Sometimes the parameter family of curves can be written in the form a theta square plus b theta plus c equal to 0. If we differentiate this parameter family of curves with respect to theta, we'll get 2a theta plus b equal to 0. So from this, we are getting theta equal to minus b divided by 2a. If you replace theta equal to minus b by 2a in equation 1, we'll get the envelope, that is b square minus 4ac equal to 0. Means if we are having the parameter family of curves in this form, then simply your envelope will be b square minus 4ac equal to 0. Note that here a, b, c may be functions of x, y. Right. Let us see the next example. Find the envelope of the family of straight lines given by y equal to mx plus under root a square m square plus b square, where m is a parameter and a and b are fixed constants. So given that y equal to mx plus under root a square m square plus b square, see therefore after grouping them, y minus mx the whole square equal to a square m square plus b square, and expand it, we'll be getting the nice form m square into a square minus x square minus 2mxy plus y square minus b square equal to 0. It is of the form a theta square plus b theta plus c equal to 0. Therefore, the envelope is 4 x square y square. Why? Because what is our capital B here? Capital B is minus 2xy, and capital A is x square minus y square, and capital C is y square minus b square. See, therefore, the envelope is 4 x square y square minus 4 into x square minus a square into y square minus b square equal to 0. So after rearranging this, we get the nice form x square by a square plus y square by b square equal to 1. That is a ellipse. So next, find the envelope of the ellipse given by x square by a square plus y square by b square equal to 1, subject to the two parameter family of curves a square plus b square having the relation a square plus b square equal to c square, where c is a constant, whereas a and b are parameter. Now for this type of problem, they will give the condition among the parameters. So use the condition and then rewrite one of the parameters in terms of the other parameters. See, therefore, the two parameter family of curves becomes one parameter family of curves, and apply the previous procedure. So in this problem, what is the condition? The condition is a square plus b square equal to c square. See, therefore, we can write b square equal to c square minus a square, and replace b square equal to this expression in the given equation, x square by a square plus y square by b square equal to 1, and we get x square by a square plus y square by c square minus a square equal to 1, which gives a power 4 plus a square into y square minus x square minus c square plus c square x square equal to 0. Let us assume that theta equal to a square. Therefore, the above expression becomes theta square plus theta into y square minus x square minus c square plus c square x square equal to 0. Now it is of the form a theta square plus b theta plus c equal to 0. Therefore, the envelope is y square minus x square minus c square whole square minus 4x square c square equal to 0. These are all some simple examples. You can refer the textbook by Engineering Mathematics by B.S. Grewal for more problems. Right. Let us see the next example. Find the envelope of x by a plus y by b equal to 1 subject to ab equal to c square. As I said, the parameters having the relation ab equal to c square. See, therefore, rewrite one of the parameter in terms of the other parameter. Okay, that is b equal to c square by a. And it gives the equation x by a plus y by c square by a equal to 1. After rearranging this, we get the equation a square y minus ac square plus x c square equal to 0. Again, it is of the form capital A theta square plus capital B theta plus capital Z is equal to 0. So therefore, the envelope is minus c square whole square minus c square whole square minus 4xy c square equal to 0. After cancelling the common term, we are getting 4xy equal to c square. Right. Thank you.